Hello everyone. Through our previous studies, we have learned the working principle of turbines. So what does a turbine look like? Today we'll learn about the structure of the turbine body. The basic body of a turbine consists of rotating pumps and stationary parts. The rotating pumps include moving blades, impellers, main shafts, and couplings, among other components. The stationary parts include the cylinder, diaphragms, diaphragm sleeves, steam sails, bearings, and other components. The stationary part of the turbine, the cylinder. The extraction pipes, exhaust pipes, drain pipes, etc. are connected. According to the high and low working pressure, the cylinder is divided into a high pressure cylinder, a medium pressure cylinder, and a low pressure cylinder. The cylinder is a shell of the turbine, separating the steam from the atmosphere with the shape of a cylinder or cone. It's usually horizontally split, with the upper and lower cylinders connected by flanges and bolts. Modern turbines also have non-horizontal joint cylinders. The inner wall of the cylinder is installed with diaphragms, stationary blades, steam seal rings, and other components. Externally, it is connected to the steam inlet pipe. For example, a 600 megawatt turbine has 4 cylinders, one high pressure cylinder, one medium pressure cylinder, and 2 low pressure cylinders. All cylinders use a double layer structure with an inner and outer cylinder. The reason for using a double layer structure is that the turbine cylinder is subjected to high pressure and temperature. If made as a single layer cylinder, the cylinder wall would need to be thickened, and the unit would experience significant thermal stress during startup and shutdown, even causing cylinder deformation and bolt breakage. With a double layer structure, the huge steam pressure that a single layer cylinder would bear is distributed between the inner and outer cylinders, thus reducing the pressure and temperature difference for each layer, making the cylinder wall and flange correspondingly thinner. During unit startup and shutdown, thermal stress is reduced, shortening the startup and shutdown time, and improving the load adaptability. Therefore, high parameter, large capacity turbines use a double layer cylinder structure. Second, the nozzles. Adjacent to the diaphragm nozzles and the stationary blades, the steam passage formed by 2 stationary blades is the nozzle, which is a crucial component of the turbine's flow path. It is used to convert steam thermal energy into kinetic energy. In reaction turbines, the diaphragm is called the stationary blade ring, used to fix the nozzles and divide the entire internal space of the cylinder into several steam chambers. In impulse turbines, the diaphragm mainly consists of a nozzle diaphragm body and a diaphragm outer ring. Its main forms of composition are welded and cast. Third, the function of the steam seal is to reduce steam leakage. Depending on the installation position, steam sails can be divided into diaphragm sails and shaft sails. To ensure the safety of turbine operation, there must be a certain gap between the moving and the stationary parts to avoid mutual collision or friction. Due to the pressure difference on both sides of the gap, part of the steam will leak through the gap under the pressure difference, causing energy loss and reducing turbine efficiency. To reduce steam leakage losses, steam sails are installed in the corresponding parts of the turbine to prevent steam leakage. For example, on the right, the contours type steam sail causes the steam to experience throttling and a pressure drop. With each narrow gap it flows through, reducing the kinetic energy of the leaking steam. In the left diagram, the steam sail between the inner edge of the diaphragm and the rotor is called the diaphragm steam sail, used to prevent steam from bypassing the nozzles through the inner edge of the diaphragm and causing energy loss. The right diagram shows the steam sail at the ends of the rotor passing through the cylinder, called the shaft end steam sail, or simply the shaft sail. The high-pressure shaft sail is used to reduce steam leakage from the cylinder, minimize energy loss, and prevent the deterioration of the operating environment. The low-pressure shaft sail is used to prevent air from leaking into the cylinder. which could lower the vacuum in the condenser and affect the normal operation of the unit. In a four-bearing steam turbine, the bearings are divided into support bearings and thrust bearings. The support bearings, also called main bearings, are located at both ends of the rotor. The function is to support the weight of the rotor and align the center of the rotor with the center of the cylinder, maintaining the correct radial clearance. Between the rotor and the stator, there are cylindrical bearings, elliptical bearings, and tethering pad bearings. The structure of a cylindrical bearing consists of two half shells connected by bolts to form a cylindrical shape placed within the bearing housing. The function of the thrust bearing is to withstand the axial thrust of the steam turbine rotor and maintain the correct axial position of the rotor, ensuring the proper axial clearance between the moving and the stationary parts. In terms of structure, swing-type thrust pad segments are arranged around the bearing, with tungsten metal-lined working surfaces on the pads. Given the weight of the steam turbine rotor, the significant axial thrust, and the high rotational speed, bearings operate under high-speed, heavy load conditions. Steam turbine bearings typically employ hydrodynamic sliding bearings, where an oil film is formed between the shaft and the bearing shell to establish fluid friction. Simultaneously, lubricating oil is used to remove frictional heat promptly, ensuring the safety of the steam turbine. Next, let's take a look at the rotating parts of the steam turbine. The rotating part of the steam turbine is also known as the rotor. Its function is to collect the mechanical energy obtained by the various moving blades and transmit it to the generator. It consists of moving blades, impellers or hubs, the main shaft, and the coupling. Here is an image of the steam turbine rotor. Let's start by examining the blades. The moving blades are a crucial component for converting the kinetic energy into mechanical energy. They are composed of the blade rod, the blade profile, and the blade tip. The blade profile is the working part of the blade, and adjacent blade profiles form the steam flow channels. There are two types, straight blades and twisted blades. The blade rod is the part that secures the moving blade onto the impeller, or the rotating hub. For short blades and medium-length blades, the blade tips are usually connected together with shafts to form blade assemblies, as shown in the figure. Now let's look at the impellers. The impeller is used to mount the moving blades and transfer the torque from the plates to the main shaft. Note that hub-type rotors do not have impellers, while wheel-type rotors do have impellers installed. Third, coupling, also known as the back-to-back wheel. Its function is to connect the various rotors of the steam turbine, as well as the steam turbine rotor to the generator rotor. It transfers the torque exerted by the steam on the rotor to the generator rotor, causing the generator rotor to rotate. Commonly used couplings include rigid couplings and semi-flexible couplings. Fourth, turning gear device. The turning gear is used during the startup and after shutdown of the steam turbine to continuously or intermittently rotate the steam turbine rotor at a certain speed using external force. It ensures uniform heating or cooling of the rotor, preventing large shaft bending due to uneven heating or cooling. Before startup, the turning gear device can also check the dynamic and static parts of the steam turbine for collisions and frictions, and whether the shaft curvature is normal. Next, we'll deepen our understanding of the steam turbine by watching an animation of the structure of a 600 megawatt steam turbine. The basic body of the steam turbine consists of rotating parts and stationary parts. The rotating parts include moving blades, impellers, the main shaft, and couplings, among other components. The stationary parts include the cylinder, diaphragm sleeves, steam cells, bearings, and other components. The cylinder is the outer shell of the steam turbine. The high-pressure cylinder is supported on the bearing pedestal by catapults at both ends. The cylinder is connected to inlet, exhaust, and extraction steam pipes. The high-pressure main stop valve and control valve are arranged on both sides of the high-pressure cylinder, high-pressure outer cylinder, and high-pressure inner cylinder rotors. The high-pressure outer cylinder is designed as a cylindrical shape and is vertically divided into inlet and exhaust cylinders. The inner cylinder is vertically longitudinally divided. The stationary blade casket is directly installed on the inner cylinder. The high-pressure rotor is a solid structure without a center hole. Shaft seals are set where the rotor passes through the cylinder. The coupling is forged integrally with the main shaft. The high-pressure stage moving blades are directly installed on the hub. The moving blades consist of the blade rod, blade profile, and the blade tip. The high-pressure stage moving blades use T-shaped rows and integral shells. The intermediate pressure cylinder is supported on the bearing pedestal by catapults on the lower cylinder. The reheat steam enters the intermediate pressure cylinder through two combined steam valves on the left and the right sides. The steam that has done work is discharged from the top. The lower part of the intermediate pressure cylinder is connected to extraction steam pipes. The intermediate pressure cylinder uses a dual-flow double-layer design. Both the inner and outer cylinders are horizontally divided into upper and lower hubs. The inner cylinder is supported inside the outer cylinder. The intermediate pressure rotor is a split-flow structure. The shaft seal section is where the rotor passes through the cylinder, with the outermost part being the coupling. The exhaust steam from the intermediate pressure cylinder passes through a connecting pipe into two split low-pressure cylinders. The function of the main safety valve is to prevent the cylinder from being damaged by overpressure. The lower part of the low-pressure cylinder is connected to extraction steam pipes. The low-pressure cylinder uses a dual-flow double-layer design. The low-pressure outer the low-pressure inner cylinder, the low-pressure rotor, has two sections, each of which is a split-flow structure. The shaft seal section is where the rotor passes through the cylinder, with the outermost part being the coupling. The blade rows of the low-pressure blades are fir tree-shaped. The penultimate and antepenultimate stages do not have integral shafts on the blades. After watching the video, we have once again reviewed the structure of the steam turbine's main body. Today, we focused on introducing the structure of the turbine's main body. Our course ends here. Thank you.